Okay, so we're going to go over the practice exam too. So the first question here is asking us which of the following is a strong acid. And so you should know a basic list of strong acids. Your only answer choice here, nitric acid, is of course the answer. B is calcium sulfate, and NH3 is ammonia. So you need to know what an acid is. Of course, an acid is going to have a hydrogen atom that's going to donate basically its proton. Hydrogen is going to leave its electron and leave as a proton. And so acids are proton donors, and so nitric acid is the acid there that's listed. Okay, let's see if I can get this out here. All right, question number 2. It says chemical reaction for calcium carbonate yields calcium oxide and carbon dioxide. Is classified as which type of reaction? So we know with different chemical reaction types, if you're starting out with a single compound and it's breaking apart into pieces, that would be a decomposition reaction. So that's your answer there. Question number 3 says when mixing a strong acid and water together, it is recommended that you do which of the following? And so remember the video we watched for lab safety, you always add the acid, add acid. So you're going to add the strong acid to the water. Number 4, which of the following reactions are written correctly? And so if you look at your different answer choices here, of course your answer is A, but B is not correct because if you look here, the charges aren't balanced. Potassium has a +1 charge per atom, and there are 2 of them, so that should be +2 overall. Hydroxide is -1. So overall, the charge here on this molecule should be +1, and we know that with compounds, generally their oxidation number should add up to 0. So that's why this chemical equation is not correct. And then C is not correct because, again, a balancing charges problem here. So sulfate has a -2 charge. Hydrogen has a +1 charge. So the overall charge here, this should be an ion with a -1 charge. Of course, it's not listed as that. And so that's the problem with this chemical reaction. This one here, everything is balanced. Sulfate's -2, hydrogen's +1, so you have to have 2 hydrogens to balance out the -2 for sulfate. Sodium is +1, hydroxide's -1, sodium is +1, sulfate's -2. So you need two sodiums to balance out the sulfate, and so that is the charges are balanced. And here the charges are balanced here. So that's your correct answer for number 4. Okay. All right, number 5 here. Zoom out some. Okay, so number 5 says if 1.5 moles of nitrogen gas reacts with excess hydrogen gas, what mass of ammonia would be produced? So in this case, you have to actually write out the chemical equation. So nitrogen gas, nitrogen is a diatomic molecule, and so is hydrogen. So I would write N2 gas plus H2 gas, okay? And it yields ammonia. The formula for ammonia is NH3, okay? And so then you have to balance the equation out. So there's 2 nitrogens here. We need to put a 2 there. That gives me 6 hydrogens on the right-hand side, so I put a 3 here to get 6 on the left-hand side. Now it's balanced. And the reason why I have to have a balanced chemical equation is because I'm going to depend on the molar ratio. All right, so first I'm starting off with 1.5 moles of nitrogen over 1. And I need to convert moles of nitrogen to moles of ammonia because we're wanting to know the mass of ammonia produced. So I use my molar ratio here. So for every 1 mole of nitrogen, I can produce 2 moles of ammonia. So here's my molar ratio here, where my units for moles of nitrogen cancel out. I'm left with moles of ammonia. Okay, and then my next step is to go from moles of ammonia to mass of ammonia using molar mass. Okay, so I add up the average atomic mass for nitrogen, which is 14, and for hydrogen it's 1 per atom, and so there's 3 atoms, so it's plus 3. So I add that together to get 17 grams per mole for the molar mass, and so that's my conversion factor that I use here. Okay, so units for moles of ammonia cancel out. I'm left with grams of ammonia, which is what I want. Now I just do the math here. Multiply 1.5 times 2 times 17 over, and that's all 1, so over 1. So I get 51 grams roughly, okay? And so your answer here is going to be, there's a little deviation there because I'm rounding here. And so you might get, a little bit different, but obviously this is the right answer. It's not even close to the others, and they're not going to give you answer choices that are really close to one another because they know that, molar mass varies a little depending on the periodic table you use, right? All right, for number 6, it's asking what is the oxidation number for manganese in a permanganate ion. So this is a permanganate ion, okay? And so what I have to do here is figure out the overall charge is -1. I don't want to confuse you there. I had to put a -2 there because that's for oxygen. So then I did the math down here instead. So oxygen is going to be -2 times 4, which is -8. Okay, so we're trying to figure out the charge on manganese, and so it has to add up to a -1 because that's the overall charge on the anion. Okay, so that means manganese has to have a +7 charge or oxidation number for the metal. So +7 is your answer there. What is the oxidation number of a diatomic element? So that would be 0. We know elements that are uncombined by itself are 0. Diatomic elements are special in that they don't exist by themselves if they're not in a compound. If they're in a molecule form, they exist as H2, not H by itself. And so earlier when you saw that we did a chemical reaction with nitrogen and hydrogen gas, well, if they're in their natural state there, it's going to be N2 and H2, not N and H. Okay, so again, remembering to memorize your diatomic elements. There are 7 of them. I listed them here, and remember on your periodic table, they kind of make a little shape of a 7, kind of, like that. So, and then there's hydrogen on the other side. But anyway, there's 7 of them. So remember, whenever and this is a common mistake students make, when you're writing chemical reactions and it says oxygen, it's plus O2, not plus O. So remember, it's O2 because oxygen is diatomic. So memorize your diatomic elements. All right, so it says here if the change in the enthalpy is negative 54.74 kilojoules for a chemical reaction, that reaction is, it's either endothermic or exothermic or cannot occur. So if it has a negative change in enthalpy, it's always exothermic. Okay, if it's positive, it's endo. If it's negative, it's exo. So that's just something to remember. And you're going to be using this again next semester if you have to take chemistry. So keep that in mind. It's something you have to memorize for 2 semesters. All right, number 9, there's a coffee cup calorimetry, and it's carried out at, and that would be constant pressure. Okay, so when we do experiments in the lab, that's a variable that usually, well, it's not going to change in the laboratory, so our experiments are done at constant pressure, referring to constant atmospheric pressure, right? All right, number 10, chemical reaction that gives off energy in the form of heat is considered exothermic. Okay. Remember, chemical reactions that give off excess heat to the surroundings are exothermic reactions. Number 11, an increase in water temperature is observed when 1.97 grams of sodium hydroxide is added. The enthalpy change for this reaction is a negative 2.19 kilojoules. What statement is accurate? So you know, because the enthalpy has a negative value and it also said that the temperature of the water went up, you know that it's not an endothermic process. Okay, so you can eliminate that. So you have basically two answer choices that say exothermic, and you pretty much have the same wording here, except one says the form of heat is released into the surroundings, and the other one says the form of heat is absorbed into their surroundings. If the form of heat is absorbed into their surrounding, that's endo. Okay, and so that would be positive, not negative. So that means B has to be the answer. It's describing heat being released into the surroundings, and we know that's describing an exothermic process, which has a negative standard enthalpy of solution there. So B is your answer. Number 12 says a reaction where the products are higher in energy than the reactants is an example of what? And so that would be an endothermic reaction. And so I'm sure in your book there are some energy plots when we're talking about endothermic versus exothermic. With endothermic, remember, heat or energy is absorbed, so whenever you plot energy, okay, over the time course of a reaction, if you're starting out with reactants, with an endothermic reaction, heat is going in or energy is going into the system, so more energy is required to break up the bonds of the reactants than is released during new bond formation of the products. And so if you're starting out with an energy value here, the amount of energy you're left with as products is increased. Okay. For exothermic reactions, it's the opposite. So you're starting out with a certain energy value for the reactants. Energy is released out to the surroundings, and so you have a difference here of the products being having a value less in energy in terms of energy than the reactants, and that's an exothermic reaction. So be familiar with these curves and looking at energy plots and knowing that endothermic reactions of products have a higher energy than the reactants. And for exothermic, it's the opposite. The products have a lower energy than the reactants. And that's just due to with endothermic, it's increasing in energy because the reaction is absorbing the energy. With exothermic reaction, the reaction is being released because it's an exothermic reaction. So your energy value is going to be less for products. Okay. Question number 13 here. We did one like this in class. Let's see here. All right, so we're wanting to calculate the enthalpy of the reaction for the combustion of methane. This is number 13, using the given standard enthalpy of formation. So here we have for different compounds here, methane, water, and carbon dioxide. They gave us the standard enthalpy of formations for those. They're wanting us to calculate for the combustion of methane. So you have to be familiar with the chemical reaction for the combustion of methane. What is methane? The formula for methane is CH4. Okay, with combustion reactions, you know a reactant is always oxygen. And when you have a fuel that's a hydrocarbon, the products are always going to be carbon dioxide and water. So when you're determining the standard enthalpy of reaction, remember it's going to be the coefficients times the standard enthalpy for that compound, okay, of the reactants added together minus, again, the coefficients times the standard enthalpy of the products, reactants added together as well. Now for O2, because it's a pure molecule, it's going to be 0. Okay, so they didn't give us that value there because it just would have been 0. So in order to do the calculation here, so we're going to, so I wrote out the chemical reaction, and then I had to balance it out. So I had 4 hydrogen on the left-hand side, but only had 2 originally, so I had to put a 2 here to have 4 hydrogen on both sides. And then there's 1 carbon on both sides. And then for oxygen, there's 2 here plus 2 there, so that's 4 total. And then on the left-hand side, I had to put a 2 here in order to get 4 oxygen on the left-hand side. So now my chemical reaction is balanced, and that's important because remember I have to multiply the coefficient times the standard enthalpy of formation. So you use the products first, right? So It's going to be 1 times the standard enthalpy of formation of CO2 plus 2 times the standard enthalpy of formation of H2O. So products minus the reactant. So here waters or oxygen is just going to be 0. Methane is going to be 1 times the standard enthalpy of formation for methane. Okay, so I substitute in my numbers here. So 1 times standard enthalpy of formation of CO2, which is the negative 393.5, plus 2 times water, which is negative 285.8, okay, minus 1 for methane times standard enthalpy of formation for methane, which is negative 74.60. Okay, do the math, and I get a negative 890.5 kilojoules per mole, which is what our answer is. All right, for number 14 here, I'll try to zoom back in and see better. All right, so it says provide the element name with a ground state electron configuration of 1s2, 2s2, 2p4. Okay, so when I look at an element that ends in 2p4, so 2p1, 2, 3, 4, well, that's oxygen there, and so your answer should be oxygen. Okay. Number 15, due to periodicity, which element would you expect to behave most like sodium? If you look at where sodium is located on the periodic table, sodium is found in group 1, okay, and then look at your answer choices, okay, calcium, aluminum, and potassium. So calcium is right here, aluminum's over there, and potassium is right below sodium. So we know that elements that belong in the same group are chemically similar because they have the same they have similar electron configurations. And so it's potassium is listed in that same group simply because its electron configuration is the same and it reacts the same chemically. They have similar chemical characteristics in that they react similarly. And sodium and potassium are both very highly reactive elements. And so potassium, of course, is your answer because it's basically found in the same period. And so it has the same number of valence electrons and so on. Number 16, which of the following has the longest wavelengths? And so we know microwaves have longer wavelengths than UV light and X-rays. That's your answer. Let's see. Number 16. All right, number 17 here. Elements in group 17 are considered, and they're called the halogens, right? Which of the following sets of elements are most similar to each other? And I said earlier, elements that are in the same period are more similar. Here we have hydrogen and helium, they're in the same row. Carbon, nitrogen, oxygen, fluorine in the same row. Fluorine, chlorine, bromine, iodine, these are halogens all in the same group. Okay, so these are the ones that are most similar because, again, that's why they call elements that are in the same group, they call them, they have their own family name, right? The halogens. And that's because they act the same. All right. Number 19 here. It says during a UV visible spectroscopy experiment, a student notes a wavelength peak of measurement at 280 nanometers. What region of the electromagnetic spectrum was this peak observed? And so 280 nanometers is in the UV region. And so here's a general breakdown here. In the visible region, light is around 400 to 800 nanometers. In the UV region, it's about 200 to 400 nanometers. Number 20, how many subshells are found in the second energy level or shell? So if you look at your periodic table here, you see for group for period 2, energy level 2, there's the S and the P subshells. For 1, there's just S. For 2, there's S and P. For 3, there's S, P, and D, and so on. So, but what your answer should be 2 for the second energy level or shell. All right. Part 2, it's short answer questions. And so just be prepared to have to, like, for example, write electron configurations for different elements. Here we have the electron configuration for a copper atom. We're trying to figure out its electron configuration. So copper is one of those ones here that's in the D block, but it's very close to having a full shell. Remember, it's one of those exceptions where it wants to have a complete full subshell in the D block. And so what's going to happen is it's going to be a little bit different than what you would originally expect. So the electron configuration for copper would be starting out with argon, right? And then 4s2 3d9, but it's not exactly that because it's almost a full shell. So anytime it's at 4 electrons or 9 electrons, it wants that extra. It wants to have a full D subshell. So it's going to pull 1 electron from the S subshell. Okay, so it's going to be Ar 4s1 3d10. Okay, so that's your answer there. Ar 4s1 3d10. All right, number 22. In what block, group, and period on the periodic table can the atom with a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5 ground state electron configuration be found? So if you look at the last term here for your electron configuration, so it's going to be in the P block, all right? So that's all the answer choices have P block. Group 7A, okay, because 4p5, you look at what that is, 4p5, that's bromine, okay? So it's in group 17A, 17 or 7A, okay? So remember that there's 2 different ways of naming groups. You can name them the new way, which is 1 through 18, or the old way, and this would be 7A. You have A and B type elements in that sense. So group 7A, that's both answer choice. All answer choices have that again. And then period, and so period 4, because look, it has 4 right there. So that's your answer. Of course, the last term is telling you that information. Number 23, it says according to the periodic trends, which metal has the highest ionization energy? So if you look at your answer choices here, well, first of all, let's talk about what is highest ionization energy. We know ionization energy is the amount of energy it takes to remove an electron from an atom, from a neutral atom. So if you look at lithium, cesium, and rubidium, lithium, cesium, and rubidium, they're all group 1 elements. And so remember the trend for ionization energy, as you go from the top down, ionization energy decreases because the size of the atoms get larger. So it's a lot easier to remove an electron from a larger atom than it is from a smaller atom. So a smaller atom would have a higher ionization energy. And so lithium, since it's highest on the periodic table compared to cesium and rubidium, that means it would have the smallest size and have the largest ionization energy. So lithium is your answer there. Number 24, a chemical reaction that absorbs energy in the form of heat is considered what? And so a chemical reaction that absorbs energy in the form of heat is considered an endothermic reaction. All right, number 25 is asking you how many mole ratios can be correctly obtained from the balanced chemical equation. So in this case, you have to come up with every scenario. Okay, so it could be 2 over 4, all right, or 4 over 2, 2 over 3, or 3 over 2, and 4 over 3, or 3 over 4. All right, so there are 6 possibilities. All right, so that's where that comes from. And again, you know, your ratios can be one way or flipped over the other way. Okay, so those are all the possibilities for that equation. All right, number 26. which precipitate forms when mixing copper 2 sulfate and sodium sulfate. So here I wrote out copper 2 sulfate and sodium sulfate. And you look at the products, they're exactly the same. Because here I have a double displacement reaction, and you know that the outsides react together and the insides. So you have copper sulfate and sodium sulfate. You end up with the same thing, and they're all soluble. And so that means that you don't have a precipitate that forms, right? Because you're starting out with aqueous reactants and you end up with aqueous products. All right, number 27, here you're given the volume, 250.3 liters of hydrogen gas. You're given the density of hydrogen gas, and it says reacts with an excess of nitrogen gas. What mass of ammonia would be produced? So again, I'm having to write out my chemical reaction. So hydrogen gas is a diatomic molecule, nitrogen gas as well, and then it produces ammonia. So again, I'm having to balance my equation. So I have 2 nitrogen here, so I put a 2 there. 2 times 3 is 6. So I'm having to put a 3 in front of the hydrogen to get 6 hydrogen on the left-hand side. So the first thing I'm going to do is take the volume and multiply it times the density to get the mass of my hydrogen gas. Okay, so this is the mass of hydrogen gas that I have. Okay, so now I can start my stoichiometry here. So starting out with the mass of hydrogen gas, and my molar mass for hydrogen is 2 grams per mole. So my units cancel out for grams of hydrogen gas. I'm left with moles of hydrogen. And now I use my chemical equation to find use a molar ratio to convert moles of hydrogen to moles of ammonia. Okay, and so for every 3 moles of hydrogen gas, I can produce 2 moles of ammonia. And so my units here cancel out. I'm left with moles of ammonia. And then I need the molar mass of ammonia, so I calculate that. Well, that's 17 grams per mole. I calculated that earlier. It's 14 plus 3, which is 17. And then now, all I have to do is do the math. 22.501 times 2 times 17 divided by 6. And I get 127.5 grams. Okay, so your answer was 127 grams. Okay, so that's how you would do that problem. Number 47. Number 28. Here it says, which is the correct balance reaction for the combustion of methane? So unfortunately, I had erased the answer choices. This should have been a multiple choice answer or question, and you should have multiple answers at your disposal, and you didn't have any. Unfortunately, I erased the other answer choices. But obviously, this is the correct balance equation for combustion of methane there. Number 29 is a calculation here. We're starting out with wanting to know how many moles of sodium hydroxide are needed to neutralize 50 mLs of a 0.235 molar hydrochloric acid solution. So we have to again write out the reaction. Sodium hydroxide plus hydrochloric acid yields sodium chloride and HOH, or water. This reaction was also used in one of our labs when we did the titration lab with sodium. We did it with sodium hydroxide and a weak acid, but we looked at this reaction as well as an example. All right, so anyways, we first need to figure out how many moles we have of HCl, right? So we have a volume and we have molarity. So we know molarity is moles of solute per liter of solution. And we have a volume, so that's the way we can find the moles of hydrochloric acid. When we do the math here, we get 0.003525 moles of hydrochloric acid. So now we need to use our molar ratio to convert moles of HCl to moles of sodium hydroxide, because that's the original question: how many moles of sodium hydroxide are needed to neutralize the acid? And so we can see here, because it's a 1-to-1, for every 1 mole of sodium hydroxide, we need 1 mole of HCl. And again, this is a balanced chemical equation. I didn't have to add any coefficients because they're all 1-to-1. Okay, so here it's 1-to-1 as well. And so the number of moles of Sodium hydroxide is also 0.003525 moles. Okay, so this is your answer here in scientific notation. 3.53 times 10 to the negative third moles. Okay. Number 30, which compound is insoluble in water? Calcium carbonate's insoluble. These guys are not, because here are the exceptions. Group 1 metals are always soluble. And then number 31, our bonus question is asking for the density of a 0.354 molar solution of ammonium sulfate. So density is equal to mass over volume. Okay, so here we're starting out with 0.354 moles per liter of ammonium phosphate. So ammonium is NH4 plus, and phosphate's PO4 minus 3. So I need 3 ammonium ions to balance out the negative 3 charge on the phosphate. So this is the molarity here, so that many moles per 1 liter. Okay, so I know 1 mole, I calculated the molar mass. Here I calculated the molar mass for ammonium phosphate, and it's 149 grams per mole. Okay, when you do the math, you get 52.74 grams per liter, or when you here your answer is in grams per milliliter, so when you do the conversion there, it's the 0.0523 grams per milliliter. All right, so it doesn't specify the unit, so either one of these would have been fine if you stopped here on the test, that would have been fine.